Okay, so good morning. Like everybody, I'm going to summarize first what we did last time, just to warm up a little bit. So the talk was about configurational entropy in supercooled liquids. And so I took quite a bit of time to go through the basics again to justify why we would care about configurational entropy in supercooled liquids. So I described the phenomenology and everything, and this is not the notes, okay? These are the notes. And so I pointed out that the dynamics, of course, is very interesting, but the thermodynamics may be changing a lot, in particular the configurational entropy in these liquids. Then we had a lot about theories and models, and Francesco Zamponi has twice emphasized the mean field theory and why the complexity and metastable states and how many of them you have is, from the mean field perspective, really driving the phenomenon of the class transition. And we have already discussed several times the tools that the theory is giving us to compute and measure something in finite dimensions related to configurational entropy. Then we went into basics of computer simulations, and I introduced the basic method for molecular dynamics that you can learn by yourself in many very good books. And then I emphasized two key features that will reappear today several times, because we will go into more details about how to measure configurational entropy. One key feature is the idea that if you go to finite dimensions, you have to deal with the crystal, at least in dimensions 2 and 3, that I'm going to consider in the lecture. So we heard yesterday that in larger dimensions, perhaps crystallization can be forgotten for good. In 3 dimensions, to fight this, we have to introduce these mixtures, and either discrete mixture or continuous polydispersed systems with a continuous distribution of sizes. And that will be very important for what I'm about to say today, the idea that if you introduce this polydispersity that's necessary, then you face new problems that you have to then solve to go to the configurational entropy. So that was one key feature. And of course, the second key feature is that you want to study slow dynamics, hence dynamics is very slow. So it takes a lot of time to do these simulations of glassy dynamics. And we ended, I think, the discussion by concluding that if you want to do very careful simulations at low temperatures in a system where thermalization and dynamics is very slow, it takes a lot of time, and it's really hard to check that you have thermalized your system. So let's assume that you have learned all the basics of doing computer simulations. So now you now have run your trajectories for long enough times. And so we are ready to go into measuring physical quantity. And this is where I'm going to start today. So I'm not sure that I really kept the numbers as in my notes, but let's assume I did it. So now will be about how to measure the physical quantities, and I'll try to go as quickly as I can to the core of the lecture, which is the entropy. So measuring physical quantities. Okay, so we have defined a lot of macroscopic observables or experimentally accessible quantities last time, related to structure factor and density correlation function, intermediate scattering function. So the first few minutes of the lectures will be like this. So you have done your simulation. So the outcome of your simulations will be, as I wrote last time, a complete set of positions and velocities for all the particles at all times. Okay, so this is for all times between 0 and how long you have simulated your system, and you have the position and velocities for all the particles. And this is n particles. So what I'll do very quickly is go from the position and the velocities, which is all that you have, because you don't have a calorimeter or something in the simulations, and we want to go to the configurational entropy, starting from the knowledge of velocities and positions, and mostly positions. So what I had introduced first, I'll go very quickly last time, is I had talked about density fluctuations and the density field. So in terms of the positions of the particle, the microscopic density field at a given time, at a given position in space, it's simply what you had probably at the very beginning of the school by Chandan, is the sum of all these delta function. So that's the microscopic expression of the density field. So from the positions, you can construct the density field, and we will move to larger scale towards measurable quantities measurable in experiments. So from the density field, you could be interested, of course, in the average density, which would be rho zero, which is the quantity that was the first line of Francesco Zamponi's lectures. That's the average number density. So that's for the average. You could be interested in the fluctuations. And again, I'll go quickly because you probably had all this already done. So for the fluctuations at position r and time t, you would just subtract from the density the average. And then you would be interested in 2-point density correlations. And that's the quantity to describe the structure that everybody has used heavily, in particular in the mean field calculations that Francesco Zamponi described. That's the key features of the liquid that you have to know and compute first in order to do the more complicated calculations that he did. So in generically, you would define the quantity like this. I'm just writing definitions without doing much with it. Just to fix my notations and go very, very quickly to the entropy. So you would like to introduce a quantity, which is a 2-point density correlation function. And if you plug this sum into this and you look at the non-trivial terms, one of these non-trivial terms will be the pair correlation function. So you have a trivial term, which is a delta function. You have a trivial term, which is the minus rho square that comes from that square. And then you have the pair correlation function that Francesco Zamponi has used heavily. Okay, so that's how you would define it. And this guy is the pair correlation function. Okay, so if you know the positions, you know the density field, you know this, and then you know the pair correlation function. So you're almost there to compare to experiments in terms of quantities that describe the structure. And in the first lecture, as I said, in an experiment, you would look at the structure factor, which was defined in terms of density fluctuations in row space. Am I allowed to write on the wet board, or it will be hard to erase, maybe? I don't know. I'll go slowly. So that's the quantity I said you would measure in an experiment, and in terms of this quantity that we now know how to compute because we know the positions and the density and everything. So I'm just writing definitions for the sake of it. So it's 1 plus rho 0 times the Fourier transform of, so I'm skipping that line, dr, dqr, and then this is g over minus 1. Okay, so we now have the structure for this system. So we have done the simulations, then we got the structure. So we want to move to the entropy, so we have to learn how to measure thermodynamic quantities. And so for the simple thermodynamic quantities, again, once you have G over, then you can compute, say, the energy or the pressure. Maybe just for the sake of it, because I'm going to use the pressure in a minute, you just write the macroscopic definition of the pressure, you plug in the density field into it, and for instance, you would get that the pressure, again, just for the purpose of the discussion, will be expressed directly in terms of, again, the pair correlation function, R, and this is dV by dr. Okay. So provided you know the interactions, the pair interactions between the particle, and this is the pair correlation functions that you have just measured, then you can go up and you can measure all thermodynamic quantities that you like the pressure. So you've done your simulations, and in 2 minutes you've learned how to do these thermodynamic measurements like the energy, the pressure, and everything. Okay? So that's how you would do your simulations. So let me make a detour because then I will introduce a quantity that will be used a bit more frequently in the third lecture, which is the overlap that we've heard from the replica calculations. So these are all static one-time quantities. Of course, you can measure correlation function in a simulation. So typically, you would like to measure two-time correlation functions, which would be, say, the time correlation between one observable at time t and at time t prime. So typically, when we do the calculations, this guy would be the ensemble average. That if you take many independent systems drawn from the Boltzmann weight, and this is how Francesco does the calculations on the blackboard, and then you would do averages over these guys. In simulations, we don't have an infinity of independent configurations drawn with the Boltzmann weight, so typically what we do instead is we replace this ensemble average by a time average. I'm just writing it again for the sake of the discussion. And this is again related to what I said yesterday, that in order for this to be converging, then, okay, so this is the function of t minus t prime for a time translational invariant. So you can forget about the two time, and this is a one-time quantity. And what you have to do is, of course, take the limit of very large simulation time, and you replace your ensemble average by a time average. And so what you are implicitly or explicitly using is, of course, the ergodite hypothesis that says that you can replace your ensemble average by a very long time average. So this is where the question of how long is a simulation, and did you simulate long enough the trajectories to have a good sampling of your configuration space is coming back to apply this and to say that you have measured the proper correlation function. The simulations need to be very long. So they have to be long enough, and how long is, again, in the eye of the guy who is checking if it's long enough. Okay, so just to finish my slow introduction to these things, the quantity that I had discussed in the experimental introduction is the intermediate scattering functions. Okay, which you can then directly compute from the particle trajectories. I write the definition once more. You've seen it several times already. RIT minus RJ 0 wave vector Q. Yes? So you want to start from something, do a trajectory somewhere, and then? So this is time 0, this is time t, and then you do what? And how do you do different realizations? How do you do another simulation? Yeah, so it means you have to produce another totally independent configurations that you would run then t. And if you want to do this ensemble averaging a lot, you have to produce many of these initial conditions and then do many of these trajectories. Well, it is practical, you can do it, but you have to remember that if you want to produce independent configurations at long times, how do you do? You have to do simulations that's separated by very large times to produce these configurations. So you already have done this. Okay, so to produce the initial conditions, you have to work anyway. Okay, so depending on the problem, you may decide to do many short simulations, but you have to do them, or you do one long for a very long time, but the amount of CPU time that you've spent is the same. I know what you want. So in terms of the cumulative CPU time is the same if you want, and you have 1,000 computers, you do 1,000 simulations at once. Well, again, you have to produce these initial things. So it's the same. The effort is the same. Now, the human time involved. The effort you have to make at the end, it's the same for the computers. Now you can try to manage that more or less efficiently from the human's perspective. But in terms of the conceptual CPU time, it's strictly equivalent what you're proposing. I'm sorry. So we went into the intermediate scattering function, which is these collective quantities. So most of you doing simulations, they typically replace this by a sum of just one particle, and you look at single particle displacement. So that would be the self part. Or you could look at just this guy squared, that would be the mean square displacement that Francesco has described in his lectures. So I don't want to do this today. I just want to see that what you're doing here is you're looking at how density fluctuations of a given wave vector Q, sorry, that was 0, is relaxing as a function of time. So you start from a given density profiles and you see it relax as a function of time. So it means you're comparing the density profile at time t to the density profile at time 0 at a given wave vector. So from the computational point of view, there is a quantity that captures exactly the same physics of comparing two density profiles at different times. But let me introduce it now, because in the dynamical context, it's very natural, because it's strictly speaking the equivalent of the intermediate scattering function. I'm making a parenthesis and then an average. So you again take your density profile at time t, the density profile at time j, and you ask yourself, are the two density profiles the same? So if the time goes to 0, you always find a particle in front of particle I at time 0, and the self-time is giving you 1. So by definition, Q of t equals to 0 is equal to 1. So that function is a Heaviside function. Okay, and if you think carefully about this function and you go to very large times where the density profiles at time t is totally uncorrelated from the one at time 0, you see that this function goes to a very small quantity. Okay, so it's very, very small. It's just related to the density, I think. And this number A that I have introduced, which is a length scale. So A is a length scale. Okay, and so the physical content of this quantity, it's almost the same as this one, provided that A is taken of the order of 2 pi divided by Q. So the overlap function is comparing density profiles at time 0 and at time t. It goes from 1 time 0 to a very small number at time infinity, and it's telling when the density profiles are decorrelated. And that's the quantity which is called the overlap that I'm going to use to compare density profiles without the time now to measure this transparency potential in the third lecture by comparing density profiles in 2 independent configurations. So that will be the microscopic definition from the computational point of view that I want to study. And I will have to choose a little bit carefully what length scale I want to introduce to compare these density profiles. And typically I will take something which is of the order of the relevant wave vector that we have in this simulation. So typically in the simulations, we will take this to be a small fraction of the diameter, and that's typically related to what Francesco has repeatedly called the gate size. So that's typically these thermal vibrations that you have in these systems when they are rested. So the idea of the overlap is really to compare density profiles up to the thermal vibrations. And in the context of measuring the dynamics, it's a very interesting quantity because it's much less noisy than the intermediate scattering function, but it has the same physical content. So I like it much better even for the dynamics. And that's the one I'm going to use for the step. So we have the dynamics, and to introduce the end of this lecture, let me say a few words about how many decades of the slowing down of supercooled liquids you can follow and measure, being faithfully and comfortably in equilibrium conditions according to the criteria that I defined last time. So if you go through papers that have been published over the years, so there are papers that I really like from the beginning of the 90s by the Hansen-Barra group, where they studied a binary mixture of subspheres. And if you look at the figures for the time correlations functions, they have about 1 decade of glasses slowing down in these papers. And I'm really generous because Jean-Louis is my supervisor. So it's a very short time window that I have been able to simulate at the time. Now you have well-known computational papers from the mid-90s, so just a few years later, people have been running simulations a bit longer, so Walter Kopp in particular. And if you look at the range of glassy dynamics that he gets, it's something like 2.5, 3 decades at most of interesting glassy dynamics that he can follow before running out of computational steam. And then I quote 2009 because it's a paper that I was part of, but it's in collaboration with the experiments performed on hard sphere colloidal particles, and we were reaching roughly the same numbers of glassy decades. And we have reached something like 5 decades. For super simple models like hard spheres in 3 dimensions, that's 5 interesting decades of glassy dynamics. So Walter Kopp was very much interested in trying to approach the MCT, the dynamical transition, in the language of Francesco Zamponi. In 2009, what was nice from the experimental point of view is it's slightly beyond the MCT, but not by much. Okay. So it's beyond, but just 1 point is beyond, but at least the experiments are clearly beyond. So that's roughly what you can achieve, and maybe you can do 1 or more decades since 2009, but that's roughly what you can do. So I remind you that in the experimental plot that I sketched on the lectures, they have 12, 13 interesting decades of glassy dynamics before falling out of equilibrium for molecular liquids. So from the point of view of molecular dynamics, simulations of molecular systems, we are far from the experimental glass transition. If you look at experiments performed with colloids, if you have small enough particles, maybe you have 5 decades, but if you go to these experiments where people look at the colloids and have much larger particles that move much more slowly, they have roughly 2 decades of glassy slowing down, and depending on the size of the particle again. So from the point of view of colloidal physics, we are very much stuck in the numerical regime, extremely far from the experiments, and that's the numbers that I would like you to remember for the end of the lecture today. Okay, so we've done the simulations, positions, density, percorrelation, thermodynamics, dynamics, everything, up to a temperature where we can simulate close or beyond the dynamical transition. So we are thus ready to go into the core of what I would like to discuss is what about entropy? Okay, and so the first thing that I would like to sketch is how you measure, first of all, the entropy of the liquid, not yet the configurational entropy. So I'll just describe very basic things about how you get, first of all, the entropy of the liquid before subtracting anything related to vibrational or crystal or whatever, as we defined from the experiments in the first lecture. So the basic equations, and again, I'll try to go quickly because I want to do relatively many things today, is you start from the definition of the free energy in terms of the energy and the entropy. So from this, you get, of course, then I'm trying to follow my notation from my notes. you get the entropy as the difference between the energy and the free energy. So the energy, I've told you, you can compute directly from your simulation. So what we have to learn in the next minute is how you would measure the free energy, the total free energy of the liquid. So this is done into several little steps that I'm going to write explicitly. So you will decompose your total entropy here into two quantities. One, which is the entropy of the same system without in the interaction. So that's the ideal gas entropy. And here, this is just the excess entropy that comes from the particles interacting between themselves. So it's like you take the system to zero density, and then you get the ideal gas, and then you have to add the interactions. So that's how, one step to compute the total entropy. So it's all very, very basic. So that was a mistake. Oh. It's going to be okay, don't worry. After a few layers, it will be fine. Okay, so the goal is I want you to have all the definitions to say that you have all these steps, at least carefully written in your notes. And then if you want to do a calculations, you can do it. So the way I will be using to measure the free energy is by using this thermodynamic definition, that the pressure is the derivative of the free energy with respect to the volume at constant temperature. So I told you that you could measure the pressure easily from the simulation. So it means you have access to the derivative. So if you measure the pressure for different densities and integrate, you will get the free energy. Okay, so you get F from what's called thermodynamic integration. By measuring the pressure at different densities. Okay, so that's essentially the idea. So I will just give you the expressions, then you have all you need to do a measurement of the entropy this afternoon after the lecture if you want. So this is phi minus log rho minus log of the de Broglie length plus a term that we will be discussing more carefully later. So this guy is just the de Broglie wavelength. This is a number, this is the density, and this guy is the mixing entropy. That comes from mixing the particles in the ideal gas limit of different types. And I will give you expression in two blackboard, I think. So this is needed if you have something that's not composed of monoatomic particles, monocomponent systems. As soon as you have two types of particles, you have to introduce this mixing term, which appears in the ideal gas expression of the entropy. So it's nothing fancy related to complex physics. It's just the ideal gas non-interacting system. You have to count how many states you can create by having, say, two types of particles. So it's first year thermodynamics, nothing glassy or complex. So that's the ideal gas. So now we want to go to the excess entropy. This one, 5 divided by 2. It comes from the kinetic terms and everything. It's a stupid KBT. Okay, excess, so it's beta excess energy minus the thermodynamic integral. Okay, so 0. So I integrate over the density over the volume from 0 to infinity. And then I get the excess pressure at rho prime divided by rho prime squared. So I measure the pressure, I integrate, and I get the excess entropy. And if I put these two things together, then I get the, I sum these two terms and I get the entropy at a given state point that I wanted to measure. And then I have measured the total entropy of the system. So you have all the equations to get to this guy, to get to the total entropy at a given state point, density, and temperature. So from the computational point of view, of course, it means that if you want to measure the entropy at one point, you have to do simulations at an infinite number of densities before going there. So in principle, it's okay because you want to access the glass states gradually and looking at all the points, but then you have to carefully measure everything in equilibrium conditions between the ideal gas till the very difficult state point that you want to study at the end. That means you have to do a series of carefully thermalized and sampled simulations. So this is, again, to introduce a little bit of confusion. So this mixing entropy, I said, comes from the fact that you may have a mixture. Because you need a mixture, because I want to discuss simulations in dimensions 2 and 3, I need to have different types of particles. So I have to handle this mixing entropy term, and it's a bit of an interesting story. So let me then digress on this a little bit, and for the general purpose of this, I will take an M component mixture. So for the binary mixture, M will be 2, but we don't care. And the notations I'm using for this is I introduce xm as being the number of the M component to the total number. So Nm is the particle of type M. And so xm is the ratio, is the density of these particles. And M goes between 1 and capital M, which is the number of components that I have. And if you take M going to infinity, then you can describe continuously polydispersed systems that I will do also in a minute. Okay, so what about all these mixing entropy stuff? So to see how it goes, you have to restart from the expression of the partition function for a system that has the M component and put all the factorials together. And this is what I'm going to explain to you in some details. So you have these M components, so you have this product of factorials to the partition function, and this is how you would write the partition functions. It's minus beta UR. So the details don't care. So what we will be interested in is this product of factorial. So if you have just M is equal to 1, this is the factorial n that you add in your partition function all the time. Okay, so from the partition function, you typically have the free energy. And from the free energy, you will get the entropy. So the free energy will be the log of that Z. So there will be a term in this entropy that will come from taking the log of this product of factorials. So there is a term here that comes from taking the log, and the product is at the bottom. So you have to take minus the log of this product of M factorials. So one of the terms that you have in the log is this one. And that's the one that I would like to discuss because this is the one that goes into the mixing entropy in 1 minute. So you use the Stirling approximation for the factorial. You put everything together, and these terms here, I'm just trying to speed up a little bit the calculation maybe. So you have a term that just groups all the n, and then you have a term that you can rewrite like this. So it's xm log of xm. So this time it's the same as in the monocomponent system. Okay, so this one is already included into the ideal gas expression that I have introduced before. And this is the term that only arrives when xm is smaller than 1. Otherwise, it disappears and goes to 0. So that's the mixing entropy. So if I put n times this, I don't know. So this is the definition of the mixing entropy that I have added to this one. So it just comes from the combinatorial of the different mixtures. So a few things you should No, and I'm trying to justify why I'm taking so much time with the ideal gas. So if you take a binary mixtures of two types of particle, and you take a 50-50 composition, for instance, you compute this S mix. And so you have minus 1/2 log of 1/2 minus 1/2 log of 1/2, so it's tons of log 2. And log 2 it's something like 67693. Okay, so that's the value of the mixing entropy term that you have to include in your calculations of the total entropy of the liquid. I haven't given you those numbers the other day, but when I presented the plot by Kautzmann of the configurational entropy going to 0, I rescaled everything so that it starts at 1 in the high temperature liquid. I haven't given you typical numbers from experiments for the configurational entropy at this onset of slow dynamics, but if you look across the variety of liquids that you find experimentally, the value of the configurational entropy at high temperature is typically 2 or 3. It's of the order 1. Okay, so, and what you do later is you want to follow the configurational entropy that decreases by a factor 2 to 3 in experiments. So you get from 3, say, to 1. And you want to extrapolate when this quantity goes to 0. So because the mixing entropy term is there and it's 0.7, it's a large fraction of the entropy that you have to add and subtract into your system. So you'd better be very, very careful about what you do with the mixing entropy. It's clear that if you shift all your curves by 0.7, then you'll get totally wrong results. So you have to face it, you have to discuss the mixing entropy quite carefully, otherwise you get total garbage. Okay. So what about continuous polydispersity now? And then the garbage gets really annoying. Okay, so if you have continuous entropy, it means that you have one particle per type, and so it means xm is 1 over n for all m. Okay, so you send a capital M to n. And then you represent your continuous polydispersity. Each particle is different from the other one. Okay, so where is this? So you plug this xm into the expression. So you have 1 over n, log of 1 over n. You sum your n, you multiply it by n, and you find that the mixing entropy goes as log n. So the mixing entropy is actually going to infinity. So the number that was already very big for the binary mixture that you had to deal and handle, it's an infinity for continuously polydispersed system. So naively, this is where we started to think about it, because we wanted to use continuously polydispersed systems for reasons that I will explain, I hope, before the end of the lectures. That the entropy of the liquid that we wanted to compute, it was effectively infinite. So we wanted to subtract vibrational entropies that were not infinity. So we ended up naively, at least on the paper before starting, with configurational entropies that were, strictly speaking, divergent quantities. And we wanted to see when infinity was going to 0 to measure the Kautzmann transition. So that was not good. So that's the confusion we started from. If you have one particle, yeah, it's true. So yeah, I'm going a bit fast. You're right. Strictly speaking, you're right. So you have to take the limits in the different order. It doesn't help you. Yeah, but it doesn't help you. You don't go like this. So it's all in the paper with Mizaki that I meant to mention. You're right. I'm trying to go to the interesting questions quickly. So what is a bit annoying is, if you think about the physics, it's like this. Imagine that you have a liquid that's made of, indeed, a continuous distribution of diameters, but this distribution is like this. You know, it starts at sigma, it goes at sigma plus epsilon, and epsilon it's super small as compared to sigma. So it's almost like a monocomponent system. Nevertheless, it's continuous. Then this multiplies, and it has a mixing entropy that's divergent. Physically, you would say, well, this system, in the limit of epsilon going to 0, it's really equivalent to this one, the monocomponent system. But the entropy of this one, it's not infinite, it's well-defined. When you start to think about those things, then you say, okay, there must be a solution to this, and this is what I will try to discuss. Another interesting system that we had in mind is, imagine that you have a binary mixture, which is what everybody had studied before we did the continuous polydisperse system. So you have two delta functions like this, or like this binary mixture. Okay, so you have a 50-50 mixtures of size sigma and sigma plus epsilon. And again, you say, okay, maybe if the two diameters are different, it's really a mixture, but in the limit of epsilon going to 0, you still have this 0.7 quantity in the mixing entropy, and it's only in the limit of epsilon equals to 0 that 0.7 entropy is lost, suddenly discontinuously, from the point of view of the liquid entropy. So again, if you think in terms of this thought experiment, you realize that you have to deal with polydispersity a little bit more carefully. I'm trying to erase the 1 kilometer blackboard at the same time.
So now the point that Francesco mentioned, maybe you can explain a little bit more, because even if, of course, the simple answer is if you have a large number of particles, each type will have a large number of particles in turn. So you could use Stirling, but if it's continuous, it is a I mean, does it really go to 0, go to infinity?
Francesco was asked the question. I was trying to reconstruct the other argument. I cannot in my head while I'm erasing and thinking about the note. I promise that I will give it to you at the end of the lecture.
But the other,
I looked at it as well. It's no way. It's not the way to solve the problem.
The other side of it is the work of Dan Frenkel with looking at, whether you should treat them as identical or not identical. That's probably something you're going to talk more about?
Well, that's what confused us a lot initially, because we had to digest all these 100 years of controversies with the Gibbs paradox and stuff, just to realize that it had nothing to do with anything that they had said. It's unrelated, so I don't even want to discuss it publicly. I'll show you why it goes away and how, and then when I've given you the physical interpretation of it, ask your question again, and you'll see it's not about distinguishability of everything, it's just about defining the class entropy properly. But it's not about the Gibbs paradox at all. I'm happy to take the question in some more minutes, if you want. Yes, then it gives me time to read my... I hope Misaki is not watching live from Montpellier. I'm totally ashamed. Okay. So we have the total entropy, and then I'm happy that the first row of people is there, because the first method I'm going to describe to get finally to this configurational entropy. It's a method called the potential energy landscape, and to prepare my notes, what I had to do is read the papers by Sri, and this morning I uploaded the review paper by Francesco Sciortino just to check one more thing in my notes. So, what can I teach you? Yes, I know. So shut up and do nothing. So I'm trying to go quickly to the main ideas of how you get there, just to give you the idea how these guys have measured the configurational entropy, thinking about the potential energy landscape, and I want to give you the expression so that you have the recipes in your paper, and then you know in principle how to do it if you had to do it. So the idea of the potential energy landscape is, I don't know how to go quickly to the idea, is just to take this picture seriously. take this picture, so you see. I'm not trying to make fun of everyone, Bulbul. Okay. And so you're thinking of your potential energy landscape, free energy landscape being made of many minima, complicated, and trying to make sense of it in a very practical, interesting way. And so the way that this potential energy landscape approach the configurational entropy is to think of these minima that we don't really discuss but only sketch in these cartoons as energy minima. So the idea is you identify this with energy minima. That is configurations taken to 0 temperatures, and in the language it's called inherent structures. Okay, and the reason why it's practical and interesting and it's useful for the point of view, at least of the simulations, is that energy minima don't have the ambiguities that the free energy minima have that we've been discussing all along in these lectures. You can define them in finite dimensions. You just check configurations. You go to an energy minimum. It's stable because there is no temperature. It exists. You can measure it, compute it. No ambiguity into the definition of this minima. They're well defined. And then you partition your configuration space into basins of attractions. Of these inherent structures. And this is what the configurational entropy in this approach means. So it means these inherent structures, you sort of say that this is one state. Okay? And that's your practical definition of a state. And everybody has been repeating all along the school that we don't know how to define states from the mean field perspective, complexity perspective. So here the approximation is crude, I will call one state, one inherent structure, that's it. Okay, so it means it's different from everything you've heard from the mean field perspectives or the free energy landscape complexity perspective. Because you're making this approximation, nobody knows how good or bad it can be. There are tons of discussions, models and everything, but this is where you're making the approximation, and then the rest, in a sense, it's a computational recipe that I'm about to describe in 1 minute. So the idea of this is, you say for one energy minimum, then I will have this basin of attraction that I will call alpha, and then you partition your phase space into the different basins of attraction. And then you say that you partition functions. I go back to monocomponent system for 1 minute just to simplify and cut the discussions into 2 steps. You write your partition function like this.
So can I say just one clarification thing?
I'm just finishing this line, and then I'm with you. And so you say that this is the way that you're going to compute your free energy.
No, I mean, even from the perspective of the mean field models.
Yes.
I mean, when you look at something, when you look at the p-spin model, you could, in principle, say what you want to compute are energy minima and the corresponding complexity. And there it is the same thing, because the tap minima.
The tap minima are free energy minima.
Well, but if I look at it at 0 temperature,
Yeah, but when you, it's been discussed over the last 20 years, so you know this much better than I do. Okay, so why do I do everything here? So I had planned to do it. I'll try to do a bit faster because time doesn't permit. So the idea is you say, okay, I'm going to look at the partition function of one system restricted to the neighborhood of the inherent structure. So that has very much the flavor of the constraint thermodynamics that Francesco was mentioning. Again, the constraint here, it's performed around an energy minimum instead of an equilibrium replica. And this is where the Franz Parisi approach and this approach probably differ in terms of the concept. Okay, so the Z alpha will be something like this. It's 1/n. And then I have to restrict this to the basin alpha if you want, and then that's the Rn exponential minus U or Rn. Okay, so that's what you would do, and then this comes the tricks that I will have to revisit in 1 minute. Is you think, okay, I'm picking one energy minimum here that I've obtained from minimizing the energy. If I exchange the position of all the particles, so if I do permutations of all the particles, I would get the same thing. So if I want to take into account these partitions, I have to multiply by n factorial. And I think this is exactly how you have to phrase it in your review. That's what I wanted to check this moment. That means these factorial n's disappear, and because you've heard the story of the mixing entropy and the factorial, then you know that I'm doing something here. I'm not describing immediately, but for mixtures, that will be where there is a key point. So that's what you do. So you restrict the basin, and then to go quicker, I will describe just the harmonic expression, the harmonic approximation. And if you want to look at more details, look at the review by Francesco Sciortino on harmonic effect and everything else. Okay, so the key steps is you write your energy as the energy of the inherent structure plus some fluctuations, and the fluctuations you just take the quadratic term of this. I'm just trying to go as quickly as I can, just to give you the ID, and you go to second order to this. Okay, so that's a quantity that I think has been mentioned already several times. This is the Hessian. So that's the matrix of second derivatives near this energy minimum. So if you want to do estimate these things, what you would have to do is you have to diagonalize the Hessian, and then you get all the eigenmodes and eigenvectors and everything again, and then you get something like this. These notations that I think I may have borrowed from Francesco's review. Okay, so the A sum would be the sum over the eigenmodes and eigenvectors, and I then have quadratic expressions for everything. So probably I'll go a bit faster. So you plug this into this, and you have these integrals to be performed that are Gaussian integrals. The results, Z alpha, would then be something like exponential minus beta, the inherent structure energy of the base in alpha, minus some free energy that will contribute to the vibrations near this energy minimum, beta FB. So I let you do the Gaussian integrals, and I just give you the expressions to be self-contained, -1/2 sum over A, and then I have logs, and then for reasons squared divided by n. That's just coming from the Gaussian integrals from the harmonic approximation. So we have an expression which is explicit in terms of the eigen values here. So we have this vibrational contribution to it. Okay, so that's how you would do the calculations in practice. And then I have to do this one more step more carefully. And so you have to collect now all the results from all the inherent structures. And again, this is the trick that's done all the time. So you introduce your delta function here to have an integral, and you want to finish the calculations. That's delta E alpha ES alpha. So what I've done here, I think, is I've introduced just the number 1 in front of my, Z alpha. Alpha is at the bottom. And then we exchange the sum and the integral to get the configurational entropy. So that bracket is 1. Yes, it's just the delta function. Then I invert to get the Z. I'm skipping a few lines at each time. So speed up a little bit. So I exchange the sum and the integral, and then I put the sum in front. I'm trying to stick to my notations. alpha times z. This, and this is the quantity that I want to define. So it's the number of states that have inherent structure energy AIS, and that will be the exponential of the configurational entropy that I'm after. Okay, so I just exchanged the integral and the sum. I rewrite things a little bit, and I call this quantity here, which is a distribution, the number of states with inherent structure energy EIS, and this I define the configurational entropy. So maybe to stick to my earlier notations, I should already call it Sconf. So that's the practical definition of the configurational entropy in this potential energy approach. So I wanted to say this later. So it means that in this approach, what you're trying to count is the number of inherent structures that you have. So again, in the mean field limit, the quantity was the complexity trying to compute the number of free energy metastable states that were well defined. You don't know how to do it, so you replace it by a number that you can compute. That's the number of inherent structures. Okay, so you put everything together into this partition function. You do your saddle points, and then you get your free energy and the final expression for the configurational entropy that I want to express. So you do a saddle point to the partition function, and then you get the free energy from the partition function, which would be like this. It has different terms. So it would be, I put a star for the saddle points, and these are all quantities that I hope I have defined before. Minus T, Sconf. Okay, so we have the free energy. If you look at the energetic and the entropic terms like this, you finally arrive to the expression of the configurational entropy. Which is where I wanted to go. So that's the expression of the configurational entropy. That would be the total entropy minus just the vibrational entropy. So again, I'm trying to go fast, but the concept, it's rather simple. So what you do in practice at the end, so this is the total entropy. The first part of the lecture was about the thermodynamic integration to get there. So you have the recipe to compute this guy, nothing fancy. And what you have to do, at least in the harmonic approximations, to measure this vibrational entropy is you have to, from a given configuration at temperature T, what you do is you go to the inherent structure by doing energy minimization. So you minimize the energy to go to T equals to 0. Then you compute the Hessian, then you compute the eigenvectors of the Hessian, and then have the vibrational entropy. Okay. Once you have done these calculations in the energy minima, you put this time together, and you finally have a practical definition that you can measure in simulations for the configurational entropy from the point of view of the potential energy landscape. So the remarks I wanted to make, and I have a long list, it's, well, you have to remember that you assume that the quantity that you try to compute is really the number of inherent structures that in principle may be different from the complexity discussed in the mean. Okay. Okay, so I'll maybe do this nevertheless. So one thing that I think you guys in the front row were asked each time is, okay, but I do experiment with hard spheres. How do you do the landscape? I'm not saying you asked that question, Bulbul, but I think you have received that question 500 times, Sri, and maybe 1,000 times, Francesco. Okay, so what about hard spheres? They are so different. And you really had this, 1 zillion times. So the question comes from, I think, I don't know. There are many reasons. First, people wanted to bother you. Probably they didn't like entropy, stupid reasons like that. The reason why it's a problem is because you've chosen this path to partition phase space in terms of energy minima instead of looking at free energy minima. Of course, energy minima when you have no energy at all, because the energy is always zero, it's a problem if you had stick to the definition from the mean field perspective of free energy minima, you wouldn't even ask that question at all, because hard spheres have free energy. It's a pure entropy thing. That's what the school is about. That's what Francesco Sciortino has repeated many times in his first lecture. So it's all about entropy. Then it's a free energy. And in terms of free energy, hard spheres are just a normal liquid. They are not different. The reason they're different is because you've made that approximation, and then you have to deal with these inherent structures that indeed don't have the equivalent in hard spheres. So in a sense, it's just the practical recipe that has a problem for hard spheres, not the concept at all. And so for hard spheres, again, people have invented methods to do it, and I'm again sitting, teaching in front of the guy who has studied it extensively for hard spheres in the first pro, but didn't write a review. So the method that I'd like to sketch is another recipe to replace going to inherent structures and nevertheless get the vibrational entropy for hard spheres. So in terms of the concept and how you deal with vibrational entropy, it's totally equivalent. So you can solve the problem. You just take a different practical recipe, which is the Frankel method. And I like it for many reasons these days. The first reason is that what you have to do in this method is, first of all, you take an equilibrium configuration. So this one is at positive temperature. You don't go to energy minima. And this is your reference configuration. So you're trying to look at vibrations near a configurations, not vibrations near an energy minimum. So that's solving the problem of I don't have energy minimum. You don't go to the energy minimum. So you take a reference configuration from the equilibrium, and then you look at a copy of the system. So you look at the given configuration, and you look at the following Hamiltonians. I'm going to follow again the notations. So you introduce a quantity, probably call it K, like a spring constant, say, for the Hamiltonian of the configuration C, and this Hamiltonian would be the original Hamiltonian of the system, that's the liquid, so that would be the hard sphere Hamiltonian, for instance, in that case. And then you introduce a harmonic constraint of this kind, Ri minus Ri x squared. Okay, so the positions of the particle here would be Ri, and the positions here would be Ri equilibrium. So you put a harmonic spring to tether the configuration C to the reference configuration. So again, it has very much the flavor of the constraint thermodynamics that Francesco was describing in his Franz Parisi approach. So why is it interesting? So that's the intuition of Dan Frankel that you heard 3 weeks ago, is that in the limit of alpha, of the spring constant being much larger than 1, what you have is you have harmonic springs and each particle is doing small vibrations near a given site. So you know the free energy is there. So it's a harmonic solid. Okay, so you have a good starting point from the solid. So if you do again your thermodynamic integration from the harmonic solid, you can estimate the vibrational contribution to the system by thermodynamic integration. So I have all this written down. So the idea is you start from a very large value of the spring constant, well, 10 to the something large in the simulations, where you know the free energy, and you go to a very low value so that the system does the vibration it does at equilibrium. And all along you measure the free energy and you do a thermodynamic integration. so I had planned to write down the expressions, but maybe I'll skip for the sake of time. So at least the concept is very, very simple. So you slowly decrease the value of k, you measure the mean square displacement, you do your thermodynamic integration, and you get at the end of the day the vibrational contribution to the free energy of the system. I'm going to gain space and time. Sorry? You could do for every system you like. So it's generic. I'm just saying for hard spheres, there is no recipe. You can use this one. And indeed, you're right. You can do it. Oh, for all systems. Very well, I think it's just impossible to distinguish. So if you take the carbon-dioxide mixture that everybody at this table has studied, you do all types of this harmonic, anharmonic, Frankel stuff. It all gives similar results because harmonicity is very good, and the Frankel and the inherent structure give you, strictly speaking, the same results. There is no, the recipe is very good. Yes, I'm about to say, yes, that's here. Okay. Okay, so the problem, and this is where I want to make the connection again with the ambiguities of the construction, is when you take the limit of the spring constant going to 0, then the system becomes free. And if you're in the liquid, then the system is going to move away from the neighborhood of the equilibrium configuration. So you have to stop this. And so the limit of k going to 0, it's a bit tricky. And the reason of the trickiness is we cannot do as in mean field where you plant an equilibrium system and you follow and look at the thermodynamics here. Because we work in finite dimensions where things tend to flow a little bit, even, above the Kalsman transition. So that's where the ambiguity comes, and it's, in a sense, again, related to finite dimensional effects that Patrick Charbonneau has mentioned many times. It's the idea that, you cannot define states that are infinitely long-lived. Okay, so you do this, and you stop at some point, and you do your best to justify where you stop, but it does not really commute with everything. You have to stop. And this is, again, the trickiness of something. So that's one point that I wanted to mention, and I think it's a very conceptual thing. I mean, there is no solution to this. You have to invent, again, you have to decide how you measure your configurational entropy. So it seems that then the potential energy landscape is well defined. It's just that they have made a stronger decision from the very beginning that doesn't involve tricky decisions at the end, but the tricky decisions was the first one. So that's it. So the second thing maybe is, in this approach, it's not totally clear the number of what you're computing. So at least in the inherent structure approach, you know that you're counting something and you can give it a name, it's inherent structure. Here, it's not clear the number of what exactly you have to handle. So these are two remarks I wanted to make to compare the different approaches between themselves. Okay, so what do I have in store for the last 15 minutes? What? Okay. So there is one thing that I would like to come back to is I told you how to measure the configurational entropy for the inherent structure approach, the Frankel and everything. I did it for monocomponent system. Okay. And I said if you go to mixture, then it's a bit of a mess. So let's see how it goes and how to think about it. So again, I'll try to be a bit sketchy in the considerations. So I said in the partition function, you have this product of factorials in front and the Braille and then the configurational part of everything. And all the trouble of this was coming from the factorials there. Okay. So when you do the decomposition into basins of attraction of something like close to a reference configuration for Frankelad or close to an inherent structure for the landscape, when I went into this, I said, oh, you can take the particle, exchange them, and you get the very same inherent structure. So you have to multiply by n factorial for the monocomponent, and then everything complicated disappeared. So when you have a mixture, then it means, of course, you have this that arrives, and then you have your partition function restricted over the basin of something like this, and then I made the decision for a monocomponent system to multiply this by n factorial. So here for mixture, I have to make a decision about by what number do I multiply. So I think there are two extreme cases that you can think of is if you think of, say, a binary mixture where the size of the particle would be super, super different, like very big, very small. If you take a small one and you want to put a big one instead, that will not work very well. So it means exchanges of particles would be totally forbidden. So if you cannot exchange the particles between the different mixtures, then you would like to multiply this quantity by just permutations within the species, okay? And that would be no exchange at all. On the other hand, if you think of the examples I gave you of a binary mixture where the size ratio would be close to 1 with a ratio epsilon, you would say, well, the particles are, for all practical reasons, they are the same. So all permutations should be included. Then if all permutations are possible within the different species, then you should multiply by n factorial like for the all particles can exchange. And here you would have to multiply by n factorial. Physically, this is what you would like to do. And this is how people have dealt with discrete mixtures for a long time. And for instance, in the Cobb-Anderson, people said all the particles are so different that I cannot exchange them, so I multiply by just the product of the two factorials, and you went on. Now that you have to handle also systems with, yes, but it's still an assumption that you have to test in principle. So you made the assumption, but nobody really. So you are right that the result is correct, but what I'm saying is that if you had studied a range of Cobb-Anderson models from the one of Walter, and then you were continuously changing this, at some point you would have to change decision. And when is not included in the previous recipe I gave you. That's, I think, the point I want to make. But you're right that if no exchange is permitted, then you do everything and it's perfectly fine. I'm trying to go to the physical ID. Okay. So yes, in principle, it's this. Okay, so I had this example. So let's take the example of Francesco of a binary mixture. So we take a binary mixture, and I had sigma and sigma plus epsilon here. So if we think of epsilon being very large, so you have very dissimilar particles, then you would you would not include the exchange for physical reasons to the inherent structure energy. So if you think of the contribution of this to the vibrational entropy, so when you take the log of this, if you don't allow the exchange, you will have this factorial n that cancels this one. So it means that if you have very dissimilar terms, there will be no mixing contribution to the vibrational entropy because the factorial n at the top will disappear with this one. So when you take the log, you don't have the mixing entropy contribution. So that would be the case where epsilon is allowed. And now when you think of the opposite case where you multiply by factorial n, then you multiply just by this, and this guy survives, and so you're back to the vibrational entropy. It contains the mixing entropy. If epsilon is small. Okay, so that's the physical idea that I think you wanted to put forward, and I fully agree with it. The question I would like to discuss in the last minutes, if I can, is how do you deal with intermediate epsilon, and worse, how do you deal with this, where you have both large and small epsilon in a sense? You wanted to ask something? As soon as you have this, you have to put the factorials. Okay? Well, again, if I give you the, you have to have a recipe that applies for all epsilon. That's all I'm saying. So I think you're, in a sense, too practical in the way you want to define this thing. I'm just saying, you know, you gave me the definition, and I want to apply it to a variety of systems. I can't change the definition for each system I study. You know, that's what I want to do.
You told that if you have a sigma and sigma plus epsilon, then one should not use the product of n factorial, but you use n factorial.
So okay,
that's what the message. Maybe I'm wrong, but I
was mixing physical intuition about what you should do with definitions of things. So I'm saying when you start and define your vibrational entropy and the restricted and the basin entropy, you define it, and you don't care about what system you're going to use at the end. You want to give a general definition potentially applicable to all types of systems. I'm saying if you take that definition, that's perfectly fine and has all the factorials where I put them, and you think about how to apply this to different types of systems, then you run into the physical intuition that something wrong is going to happen because you have to make different decisions or interpretations of that if you want to study different types of systems. That's what I'm saying. So I'm trying to have, and I hope I'll come to this, definition of the vibrational entropy where you don't have to think anymore. You just use it for all systems, and the computations will tell you how much exchange you can do. That's where I want to go. So I think you'll be happy at the end.
Well, we can discuss this afternoon.
So again, I repeat this. If you take this definition, you have to decide by hand what you put into this. And if you decide by hand, then the decision will depend on the systems. Decide it by hand before doing the measurement is not something that's too comfortable. So that's for the binary mixture. And I was about to say that if you now take a continuous distribution like this of particle sizes, then it seems that if you take two particles that's super close in that distribution, they could probably, by physical intuition, be exchanged in the energy minimum, whereas if I take one particle here and one particle here with different diameters, so the case of the polydispersed system, and the problem it raises is that it has in the same system both the large and the small epsilon, for which if you want to apply the recipe, you have to make different decisions. You have to make different decisions now within the same model, so you cannot do it. So that's what we have discussed a lot. So given the time is running, the physical intuition is telling us the following. Whatever the recipe you're going to adapt, what you would like to have at the end included into your vibrational entropy is the idea that this guy can be thought as the superposition of smaller distributions. So if you have an M component, or M star component, as we said, and again, it's the physical intuition, it's not yet the quantitative definition, but what we, I think about this epsilon large, you can change the system, epsilon small, sorry, large you cannot exchange and small you can. you would like to think of a continuously polydispersed system as being an effective M-star component mixtures, which is made of very narrow things, narrow enough so that you can permutate the particles within these sub-distributions, but from one distribution to the next, you cannot. That's the idea that there probably is some kind of critical epsilon above which you cannot do particle permutations. So that's the physical intuition. So we, together with Misaki Ozawa, have written 2 papers on this. Or in the first paper, which appeared last year in JCP, we gave an empirical recipe to measure M-star, to estimate M-star by some considerations that were essentially related to what Francesco and Bulbul and Srikanth have asked me repeatedly, is if you change 2 particles and the inherent structure is essentially the same, then it means that these 2 particles can be exchanged. If you change particles with different sizes and then you start to go and find a different inherent structure, then it's too big. That's roughly how we estimated M-star in this JCP paper, and we gave some practical recipe on how to do it. Having published this, then we received emails from Rome, from Giorgio Parisi, saying, well, you could do it much more elegantly. And he sent tons of emails for 2 weeks about this. So we decided to try it, and that's the recipe that I want to give you. And it just, it's a paper that just appeared. So it's another JCP paper, 2018. And the idea is to, by computer simulation, let the system tell you how much particle exchanges you can really include into the vibrational entropy. So given that I'm nearly at the end, this is probably where I'm going to stop. So the idea is to restart from the partition function of the system for the n particle system, but to include the new term that I'm going to describe in a minute. So let me write it. And again, I won't go through all the calculations, just give you the idea of the solution and why it's so very elegant as compared to what we had done before. So let me write it, and I defined everything, n and Rn. So the whole idea is to think about the partition function in a slightly different way. So normally, when I wrote the partition function, I started like this, and I didn't have this thing. So in the idea of thinking about particle permutations, we introduced that thing, and that thing is like this. That sigma n, if we think of a continuously polydispersed system, is really the list of all the diameters of all the particles. So normally in the partition functions, you only deal with the position degrees of freedom, and this is what you have typically in your Hamiltonian, and you do the sum over all the positions of the particle in configuration space. So the whole idea behind the method is to introduce also the diameters as degrees of freedom, and do the partition function by including all the permutations of the diameter. So now, this is the permutations of the diameters, and this is the sum over all the possible permutations there are. So sigma pi of n, it's a permutation of the diameter. Okay, so that's just to say that we include now the diameter of the particle into the degrees of freedom that can fluctuate into the partition function. And of course, if you can fluctuate both in space and in diameter, then the 2 partition functions are equal. So this is the new partition function. And of course, it's trivial to show that. For the liquid, when you can move the particles in space, then this is adding nothing, because you can always trade the permutations for a change in the positions. So we haven't changed the thermodynamics of the liquid. Okay, so the thermodynamics of the liquid is not changed, but now we have a way to count permutations and to measure how much entropy you'll gain by doing permutations of the particles in the vibrational entropy. One more equation for the glass, and so the whole idea is to, I'm using this new definition of the partition function, is to again introduce the sum over the permutations into the definition of the partition function here. Yeah. Yes, exactly. And so I will include this into my thermodynamic integration. And that's what I want to. It's dead. It's restarted at 1 hour 25. The clock is dead. So it's sigma pi n and Rn. So the cool thing about this inclusion of the permutations is that when I'm going to do the thermodynamic of the near the reference configuration or close to my inherent structures, in the thermodynamic integration, I'm going to include explicitly particle permutations. They will be accepted or rejected with the Boltzmann weight, everything. So the system itself is going to tell you how many permutations you can do close to the reference configurations, how many permutations are allowed by equilibrium thermal fluctuations. So that is going to count automatically particle permutations. Well, it's going to measure the effective mixing entropy. So that's the thing. So you don't have to make decisions. So I'm probably going to stop here. So it's automatically measuring how many swaps or how many particle permutations are allowed in the vibrational entropy. So we get a new vibrational entropy by thermodynamic integrations, where at each step you would both do your ordinary dynamics at thermal fluctuations, where you try to probe configuration space in terms of the positions, but you also do moves where you also try to exchange the particle diameter, so that's the swaps. But you do this just for the purpose of measuring how much mixing entropy is allowed in the system. And with this new definition, if you go through the various examples that I gave you before, if you take your particle size distribution like this, or you take your particle size distribution like this, or you take your particle size distribution like this, it's giving you automatically the right answer. So for instance, to answer your question, if you close your eyes and you apply the formula to the carbon-Anderson mixture, you realize that it was a very good idea to do the decision that you made for the mixing entropy indeed. And the cool thing with this is that we can decide at which size ratio you need to change the decision. It's just measured automatically, and you can measure smoothly how you cross over from one to the other. And the cool thing is that if we take a particle size distribution like this, then it's telling us what is M star automatically as well. So we measure mixing entropies perfectly well. So that's, I think, where I have to stop Pinaki because I lost the time. I've confused everybody. I don't know, there was not so much today, so we went from, what did I do? I started from, okay, you know how to do simulations, so you have the trajectories, so you measure everything, pressure, structure factor, everything. So you know how to measure the total entropy by doing a series of simulations, so you're there, and you have to subtract something, and you have to start to make hard decisions about what are you going to remove from the total entropy. So one type of, one family of decision is you take your reference configuration or the energy minimum, and then you subtract something related to small harmonic vibrations to it. Either you do it a la inherent structures and you look at the Hessian of the vibrations, or you do it a la Frankel-Lad where you estimate vibrations near a reference configuration. And in both cases, because you're fixing your configurations and you just move like this, you have to, on top of it, make decisions about the mixing entropy. That comes to be a problem. And I think the next two methods I'm going to introduce in the last lecture to attempt to measure the configurational entropy. they will deal with the mixing entropy in a more automatic way. We won't have to think about it too much. So we'll talk about the Franz-Parisi potential finally, and a little bit about the point to set correlation line.